Dear ladies and gentlemen, welcome to the Central Library at the Mendel University in Brno. My name is Pavlína Pancová-Šimková and I am your host. During today's Science Café, we will debate with Petr Horáček about the wood microstructure. Science Café is jointly organized by the Mendel University in Brno and the representation of the Southern Moravian region to the EU. It is also a part of our workshop organized within the Erasmus Plus project. Science Café is a discussion, it is a debate, and it's your time to challenge Petr about the research that he has, and there is no stupid question. To make sure that we address all concerns and queries, you can ask your question here at the Central Library, but also online via the YouTube channel. Now I would like to introduce Petr Horáček to you. Petr holds a senior position at the Mendel University and also senior research position at the Global Change Research Institute of the Czech Academy of Science. He has dedicated his scientific career to the investigating wood formation on the macro and micro level, and also through stress factors influencing the dynamics of wood and in part of the biomass allocation. A part of his scientific activities, he is also training a new scientific generation. I would like to start with a rather simple question. How small we actually need to become to penetrate into the wood microstructure, and what would we see while wandering through the wood? Peter, the floor is yours.
Okay, thank you for such an interesting question. But first of all, I would like to appreciate the invitation for Scientific Cafe. It's my first experience, so I hope that I'm not going to bother nobody, particularly you, Pavlína, because you are so clever and motivated guy. So how big we should be? It depends what we would like to experience, definitely. Because we can look at the tree and in a structure from a different perspective based on the scale. First, just imagine that we are standing in front of the tree itself. So we see branches, we see trunk, partly we see the roots. So in that case, we can be at least centimeters high to see the inner structure like the sapwood and hardwood or knots. So something, it seems to be quite not unique in the structure, but steady in the structure. So we see no differences. We almost see no tearings or any particle traits. So it's enough to be few centimeters high, and then we will experience almost the same structure as within any other competing material. So there is almost no difference between concrete, glass or wood if we look at this from the macro scale. But the structure of the tree or wood is more interesting because it consists on the hierarchical structure being aligned parallel to the axis of the tree. So if we decrease our height for, let's say, millimeters, then we can witness cells, cellular structure. That's quite unique, but from the nature perspective, almost any material is based on the cells. And those cells are aligned, as already said, parallel to the axis of the tree. And what we see, they are worked based on the hollow tubes. So we would see just the tubes and we would be accompanied by the round wall around us. But the masterstick of the nature lays in the layered wood structure the cell wall consisting on. So if we decreased even more to the micrometers, just being as small as the width of hair, I am lost any, but yours are nice. So if we are as big as a hair, then we see something similar to the woven structure, something like woven structure. And within cell wall, we will see first layers, but finally thing which I consider to be the most fascinating, and that's capillary system. So within the wood, there are a lot of spaces, and the area of the space, the inner space, let's say for the cube with the centimeter times centimeter times centimeter, is more than 10 football players' ground. So extremely high surface. And what I admire the most, they are not the matter, the wood consisting on, but the spaces between the capillary system. And it explains a lot for me how the wood not only structured, but how it reacts on the different climatic signals. That's my task.
If it reacts on the different climatic signals, what's the reaction? How we can actually imagine the reaction inside? Like if it draws, does the cell become smaller? What happens inside? What is the story of the individual space?
Good remark. Everything depends on the water within the tree driven by the air or with air. So at the beginning there is transpiration. If the tree stops transpire, then not only is heated and dying in the end, but the transpiration is the driving force for the wood formation for any processes standing behind the biochemistry and so on. And funny thing is that a lot of people suppose that the wood potential or turgor, I will explain later on, is not driven by transpiration but vice versa. The transpiration is driven by the turgor. That's completely nonsense, because a lot of people, particularly biologists, I apologize to anybody who is biologist, know nothing about the physics. So one of great weakness of nowadays science is that we split it, the earth, between biologists, mathematicians and physicists. And if we use the physics to explain the wood behavior, then we definitely know that wood or cells grow only due to turgor. Turgor is inner pressure within the living cells, and turgor pressure occurs due to income of the water outside the cell into growing the vacuole through the osmotic flow. And such turgor is just part of water potential. And water potential is expression of the potential energy, the differences between the pure water and water in the substances like cell wall. And such water potential ranges in the incredible high values. Just figure out that the pressure in the tire is roughly 0.2 or 0.3 megapascals. But on contrary, pressure in the wood due to transpiration is more than 1 megapascal. And during the extreme season might be even 10 megapascals. So 2 orders higher pressures than in the tire. And if such pressure breaks, then something we called embolization occurs. So back to original question. If we have transpiration, then we have some huge pressure, and such pressure causing the passive growth of the cell, because the turgor acts like the force pushing the sides of the cell wall apart. So the higher transpiration, the higher turgor, therefore the wider diameter of the cell. On contrary, if the transpiration stops, there is no turgor. It ranges roughly from 0 to 1.5 megapascal, and no new cell appears. But the story is not so easy, because cell consists not only on outermost diameter, but as well on the thickness of the cell wall. And the cell wall is not definitely driven by the transpiration, it's driven by the biomechanical reasons. Because figure out, we have long, slender, needle-like cells. For instance, spruce is a good example. Average truncates is as long as 3 or 4 millimeters, but the thickness is just couple of micrometers, so it's needle-like. And such needle-like component is pushed like a rod, so in the end something like buckling appears, something like buckling. And for to resistance against the buckling, there is really important, the mathematical form is sectional modulus of or modulus of inertia. It's known that there is a nice power function. So if we suppose that we are widening the diameter, therefore the resistance against those mechanical loads within the wood are multiplied by power 3. So small changes in the diameter of the cell means bigger and better resistance against any potential failure, including cavitation of the water column within the wood. But if the cells, due to decreasing transpiration, are going narrow and narrow, then we see new requirement for strengthening of the whole truncate against those incredibly high pressures. Then we see the demand on the thickening of the cell wall. So thickening of the cell wall is due such biomechanical relations where the tree or cell is trying to withstand such huge stresses. And if there is no photosynthesis, or it's somehow reduced, or there is stopped the flow of the saccharides in the phloem, and the demand is not fulfilled by enough amount of saccharides, then the cell stays narrow, but having no chance to thicken the cell wall, and in the end we have almost tragedy or misery, because the adjacent cells start to lean first and to crack and to split. So in the end, the consequence of the drought, there is splitting of different cells which are glued together, and if glued cells are splitted, then the only path for transpiration is corrupted as well. So here we see quite nice feedback. The higher transpiration, the better forces for the cell formation, the better capability of such forces to withstand the stresses, and vice versa.
While studying for today's Science Cafe, I also came across the article that you co-authored in 2021. And I'll believe that we actually had a similar explanation to this. The effect of the stem and root blade defects on the tree response during the static loading, the numerical analysis. So okay. What is the numerical analysis for?
Numerical analysis is anything connected to calculation, just calculation. Numerical means that we play with the numbers instead of just ideas. I am addicted to the numbers, and I like the numbers, and I like to mine the numbers to be a little bit wiser than I am. And the point of this paper is quite simply, and it's related to a completely different scale than we spoke currently. So it deals with the general threat among the society in inhabited area against the breakage of the trees. So we really admire that within inhabited areas we have a lot of trees, but due to warming or any kind of changes, the trees tend to break more often than previous. And the most important thing is that usually they fail not due to breakage of the stem or due to breakage of the branch, but usually they fail due to uprooting. And uprooting is difficult to assess because nobody of us is capable to see to below ground biomass. So the aim was first to measure something, how relates the above ground biomass with the below ground biomass, but from mechanical point of view. It's really interesting to figure out how small there is the pot which encourage the tree on the on the place, because we usually imagine that the amount of above ground biomass equals to the amount of below ground biomass, and if the crown is wide, let's say 10 or 20 meters, the same must hold true for the roots as well. That's partly true. From physiological point of view, definitely yes, but from biomechanical point of view, it's enough just to have small plate with the depth being equal or even below the diameter of the stem. So just figure out quite shallow disc, nothing more, nothing else, with the diameter which is 2 or 3 times higher than the dBH, for instance. So the tree depends on just small area of roots. They insist and capture it on the stand, and we try to analyze first the relation between dBH, for instance, and those parameters I described. And second point, we try to confirm the theoretical models by such measurements. So numerical analysis means that we had some presumptions, we built up the theoretical model, and such model is based on a set of differential equations and something like this. And anytime we need to validate the models. So we validated the model by experiments, and those experiments consisted on the traditional pulling test. So we have tree, we pulled it, and we measure first the action, so how much force we needed, and direction, so how the tree bent, but as well as how they form the rooted area. And for us, the most important parameter is the tilt at the anchorage point. So how much the tree tilt at this point? Because basic theory suppose that if the tree is anchored rigidly, then such angle should be 0, nothing else. But if the rooted plate is not rigid, but let's say deformable, then the angle is not equal to 0, and the amount is measure of the safety or probability if the tree is going to uproot or not. So that's the point of the study.
That's the point of the study. You mentioned that we are all wondering about trees in the inhabited areas. And now we also mentioned that you need to pull the test and you need to pull the tree. What the inhabitant thinks that someone comes and says, we need to see whether the tree will stand or not. Let's try it. How is your research actually, or your tests, how they are accepted?
Good point. Once again, it depends. My usual and favorite answer. If you are somebody who loves the tree, who admires the tree, who does everything to be friend and favorable for the trees, then you...
I would mean you're not very happy actually when someone comes and tells me, I'll pull it down.
But I'm thinking about a not only correct but feasible answer. And such feasible answer is that if you love the trees, still you need some tool, something that could help you to decide if it's worth to keep the tree still, or it's better to cut it and replace by something else. And instead of those device-driven methods, it's better to have quite easy tool like any forester used to use. For instance, the ratio between the height of tree and dBH. It's a simple ratio, and Forestry uses it for assessment of resistance the forest stand against the windbreak, for instance. For our case, in case of tree growing in the inhabited area, but mainly as a single tree, not in the community, but single tree, something else matter. And what else? That is sailing area, the dimension of the crown, the width and height of the crown. So we discovered it better, we discovered something, how relates the sailing area of the crown, the height of the tree, or better, the length of the arm, plus the dBH. And it's useful for both parties, those who love as well as those dislike the trees, because now we have something concrete, something which is not subjective. Because with assessment of the tree stability, tree vitality, and so on, usually people assess the tree according their guess, just pure guess. And if two people meet at the same tree, the result of their assessment might be in contrast, up or down. But with our help, we can judge them, and in the end, we know for sure what is the destiny of the tree.
Well, hopefully that they have a positive destinies. I also know that you enjoy teaching activities. So I have a question related to that before I give a possibility to the audience to cast a question. So how are nowadays students different to the forestry student Petr Horáček 25, 30 years ago?
You are polite towards my age. I'm going to start quite seriously, because I've attended this university in Brno in the 80s. And at those times the situation was not so easy as nowadays. And I have to admit that to study forestry was not my choice. Because of different reasons. I have only two options what to study. First civil engineering and second forestry, though I wanted to study biochemistry and those minor things. So you can figure out how I felt at the faculty, which was not my cup of the tea. So I spent the majority of time outside the university. I was keen on mountaineering, climbing, and so on, so I spent almost nothing at university, and to my big surprise, I graduated. But nowadays, the students are more motivated because it costs not only money, but time, effort, and so on. So if anybody decides to study at the university, he or she must be really motivated to learn something, or to learn what he or she is and what they will to do with their life. So I really like to teach students because I admire them. If I were them, I would never ever start the university education, because it has nothing to do with education. I think that any kind of information we can gain much easier, much cheaper, much more effective through the internet and all other things. But one issue is non-replaceable at the university, and that's the socialization, or acting like characters. We are trying to convince them about our truth, how to make the life better, what is the pure distance of the wisdom, how to make the guys to be wise, etc. So being in front of the students, my experience is that at least half of them are really interested what you are saying, but you are interested less about just the information or data. They are more keen in the knowledge or your wisdom. That's my experience, and that's the difference between the time when I study and nowadays situation.
So, coming on back to that the Faculty of Forestry was not your first choice.
Yes.
Where was the time when you actually start to enjoy? Enjoy to being a forester and enjoy to actually give back the wisdom that you gain in the forestry field?
When I realized that forestry is such splendid and huge discipline where anybody could fit and find his or her professional career interest. So I always tended to be biochemistry or biologist and something like this. So biology is one important issue the forestry consists on, but there are technical branches and so on. So when I realized that almost anything is covered by the forestry education, that I definitely changed my mind. And the second reason why I felt in love to forestry was when I attended the formal education and started the practitioner to be practitioner and professional. I returned back to my home country, I mean the part of northern part of Czech Republic, and I have had chance in those 80s when the forest suffered due to emission load, how to help them. So I saw the factual results of my work. It was not just learning information, data, passing exams and so on, but I saw outputs, I saw such achievements. And that definitely changed my mind.
And I believe that you start to enjoy that. Is there any question in the audience? If not, well,
Peter, you brought us in contact with your nice model of being a very small person, and depending on your size, you had the possibility to enter special spaces in the tree, and other spaces were excluded because you could be too big. If we pick up this nice model and bring it together with your even-sized colleagues, the molecules, what can you tell us about these molecules of different sizes? Which space they can enter in the millimeter, in the nanometer, in the micrometer, in the sub-micro nanometer space? What is excluded for the bigger ones, and how does this result in the later properties of the material of the wood?
Thank you for question, but you will be probably surprised by my answer, which is controversial as usual. I disagree that the properties of the wood are due to chemical composition or inner structure. I really believe that the properties of the wood are driven by the empty spaces, by the voids, by the capillary system. Because such capillary system is even dry, so without any water, or completely wetted, full of water. And if we look at the variability of the properties, and we compare the same tree species like spruce, for instance, then there is quite small variability due to chemical structure or chemical composition or anatomical structure. But if we compare the properties of the dry wood and wet wood, it's something different. Therefore, I'm more keen in the capillary system instead of macromolecules and something like this, because it decides the property. And for me, the capillary system is a fishbone for the continuum between soil, plant and atmosphere, and transpiration and the processes behind wood formation. So, sorry that I didn't tackle the question correctly or as you expected, but the lesson to be learned, the message to take home is appreciate the empty spaces even within wood.
Well, If we talk about these empty spaces, are the empty spaces the future task for your research, or what is the future task of your research?
The future task of my research, there is gaining numbers. I already witnesses that I like numbers, but one hot topic is the measuring or calculating or figuring out the pressure within the tree. And the pressure within the tree, that's the driving force for the wood formation as well, is just assessed because we suppose that there is continuum from water potential in the soil up to water potential in the air with the linear linkage between. But who knows where are the limits for the resistance of the tree or any plant species against the drought? What is the role of any components? Is there definitely based just on the resistance of the leaf or root? Or lies the truth somewhere between? And I believe that the clue for such understanding, there is the better understanding of the wood formation processes. That's the hot topic.
That's a hot topic.
Yes.
Kira.
I heard the magic phrase. Wood formation. Hello, it's Kira. I want to ask you, are the events of the global climate change depicted on the wood cells, on the newly wood cells formed, or the tree rings, or the tree growth? And if yes, how can we translate this in numbers? How can we prove that?
Something about this too. Many people could say that trees have survived all these ages, centuries, under different climatic conditions. What is the big deal now with the last years, the last century climatic impact and industrial?
Okay, thank you. And once again, it depends. It depends. If we use the tiering structure, I mean tiering widths or tiering indexes, as a trait where the climatic signal is captured, or we look at to much more details, for instance, the structure of individual cells. So our task is to learn first the language of the tree, how it tries to convince us about its truth. So first, definitely, climatic signals are captured in the wood structure, and we are those who need to learn how to depict it. Second, we are a little bit biased by the previous research done on the tree ring widths and their connection to the climate. I mean dendroclimatology, dendroecology, all bunch of analysis like response function and so on, when due to regression coefficients, our colleagues could claim that the previous winter could definitely affect the growth of the two ongoing seasons and so on. So for me, that's nothing to do with the science, because time to time we replace the causality by just correlations. And a lot of people believe only to correlation, and they believe that correlation could explain anything. That's not true. Causality is something else. So tree ring structure, I mean tree ring width, is mainly dependent on the number of the cells. So if we know how many cells emerge from the cambium, and it's driven by climatic signals, then we know how tree rings definitely react on the climate. And that's easy to describe because there are a lot of models already published on such issue, but we have started from the really beginning, so from the cellular structure, from the cells. And on the cell level, we have to distinguish or divide the processes connected to the widening of the diameter, so elongation of the cell and thickening, both being driven by different factors. So for the elongation, the decisive factor, there is definitely turgor, therefore transpiration. Nothing else, nothing more. our trees, our plots, our data show us that we can explain more than 70% of variability on the dimensions of the cells just by transpiration itself. Nothing else, nothing more. Therefore, just footnote, we are to emphasize the issue of the carbon, of the photosynthesis, about the sources, because the trees are reacting mainly on the demands, and the demand is due to water regime or particularly the nutrition regimes. So the diameter of the trachate or any cell is due to water balance, due to transpiration, so water. But the water is better explained by the availability for the plant, which is far away from just precipitation or any kind of indexes, artificial indexes prepared by climatologists, where they compare, for instance, potential evapotranspiration with precipitation, and in that case they try to assess the drought period. But the climatic drought and physiological drought are completely two different stories. And for my experience, the most decisive, there is the amount of the water in the air instead of the soil. Because water potential in the soil ranges just between -2 megapascals up to 0. But the water potential in the air ranges from the -200 to 0. So two other higher differences, and the water is definitely sucked or driven just by the air drought. So the information we read, which is captured in the wood structure, speaks more or less about the dryness or wetness of the air. So we are far away from precipitation and other things. And we talk just about the diameter of the tracheids. And the thickness of the cell wall is definitely connected to the temperature. So if we know how those factors relate to the wood structure, then the information captured there could be read.
And if we continue on that note, I mean, you are talking about reading the information, the hidden information. What are tools are the tools to be used by scientists to read such information?
That's important but sad story, because I am definitely convinced that we live in the atmosphere, in the science, which is driven by devices. So we measure only such things, the tools, the toys, the devices are available. But that has nothing to do with the data we definitely need to measure. Because once, for instance, the majority of scientists believe in the photosynthesis. So anybody bought the devices to measure photosynthesis. Nowadays, we think that the same importance we should pay towards the transpiration. So anybody is buying devices, how to measure the sap flow and etc. But in the environment where the science is driven by the devices, it's really science.
So on that note, what toy you would like to have for your science? Which toy you are missing?
Me first. Sound brain, but the models, the theory, the hypothesis. And if I first formulate the model, then such devices are needed only to validate the model, not vice versa. And the models must be based on the current knowledge, and we have a lot of. I think there is no need to measure anymore. Because first, the data are shared worldwide, so why not to ask German, Austrian or other colleagues to get access to them? And no matter what kind of data are, they are valuable and useful for validation, once again, for any kind of model. So I like the modeling. I like the advanced statistical methods. I like data mining. I do not like collecting more data with with support of more advanced devices.
Okay, so on that note, I have to have a step towards the European science policy. Sorry, that's something that I have to ask. Open science, open access. I think there is no sentence actually written without those. None would be actually set on the European scientific political science. So what's your opinion when it comes to the open science, open data?
Tomorrow, I have to defend our data management plan. We prepared in the frame of one international project connecting Czech and Norwegian partners against some providers and so on. And we did nothing else, nothing more than copy and paste. So I found some data management plan within another project, and I just changed the title of the project, and I thought that I did my work. But finally I realized that it's really hard to bring it into life, because the data management plan is not only about such regulations. It's about four important things. First, what kind of data we collect, so we have to be sure first what kind of data we collect, and if we insist, as is our case, on the external data, for instance data from climatologists, how to deal with it. Second point is any data must be accessible, not only free, accessible, including metadata. So we ask ourselves what kind of data we should share. The raw data, and anybody is potentially available to harm them, to replace, to change, to modify, or metadata only, or product, so already proceeded data. And those questions are quite important, and nobody can tackle with them, and nobody answer my question. And third, the data should be reusable. So if I paid a lot of time, effort, human resources, money to collect data, and then I am asked, for instance, by Chinese colleague, please be so kind and provide us your data. And in the end, they are not polite enough to appreciate them in acknowledgement, at least. So I am aware, why should I be open towards them? So the topic is not easy for me. To be honest, I do not know any institution in Czech Republic who has prepared a feasible data management plan. I don't know nobody. I asked a lot of people, and they said, we use FTP and some servers and so on, but that's far away from what is foreseen, for instance, by Horizon 20, because they have template, we should tackle it, and so on. So it would be nice if somebody made first step, and we other just copy and paste.
I'm not exactly sure if the data scientists would agree with you, because it's a long story, and it's a big story. And you mentioned no Czech Research Institute has the data management plan. I would take correct. I would take that on next step. So are the Czech research institutes and universities actually competitive when it comes to the European scale?
Definitely they are. Definitely they are. Not only because I am Czech citizen. I am in touch with a lot of international colleagues or institutions. But I think that our big competitive advantage lays in fact that we are not so rich as our colleagues in Western Europe, because we are not capable, we are allowed but not capable to buy what we want. So if we are restricted in our budgets, therefore we have to think twice first what we can really dare, And second, how to use it effectively. And third, in the end, sooner or later, we realize that we do not need any device. So that's our competitive advantage, I think, and therefore I think that we are still competitive to the European Union countries and the whole world, though the salary policy, turnover of staff and other issues are really pity, because how to attract somebody from Austria or Germany if I offer salary which is below something. So it's not about the money. I think that our competitiveness lies in our ability to model things, just to model things.
To model. Okay, so I give the audience now the last chance to think about their concluding question, and I also have one, and that's how often are you mistaken with Petr Horáček? The Petr Horáček, who is the author and artist living in London and actually working on the kids' books.
That's not the case, but I am often mistaken by people who think that I am the famous biologist from another Czech university who read textbook on dendrology. So there is a really nice textbook on dendrology written by Petr Horáček, so I am frequently asked to sign it, because they know that I deal with trees as well, and it's difficult for me to explain, so I have to admit that time to time I really sign it, the book, even though I was not author.
So, is there any other question in the audience? If not, then...
One last question. So, if you could be in the audience, what kind of question would you like to ask to the interviewer?
Are you thirsty? And the reply is, yes, I am.
Well, thank you for that question and the comment. And with that, I would like to thank you, especially to Petr Horáček, for dealing with our questions and to dealing with us today. I would also very much like to thank you to our technical staff who did tremendous to actually set it up and to put it online, and all of you here in the Mendel Library. And thank you for watching, and hope to see you again in another Science Café.
Thanks to you, Pavlina. You're a perfect host. Okay, goodbye.